Hi guys, welcome to a lesson of ordinary differential equations. So in the previous class, we started nonlinear first order differential equations, and in this class, we'll uh, talk about the Bernoulli's equation, and it's a specific case of nonlinear differential equation. So let's start with the general form of Bernoulli's ordinary differential equation. So the general form is given by y prime plus p of x times y equals q of x times y to the power n. So the difference between the Bernoulli's and linear first order differential equation is that in the linear equation we have on the right hand side only q of x and y to the power n. The term y to the power n is not present there, right? So this is the form of linear first order differential equation. For Bernoulli's equation, we have the standard form. And then how can we proceed is just divide the whole equation by y to the power n. So here we will get 1 over y to the power n times y prime plus p of x times y divided by y to the power n equals q of x, right? So now we can assume that u equals 1 over y to the power n, which implies that u equals, oh, sorry, not like this. First of all, we will simplify this equation. So here we can write 1 over y to the power n as it is, y prime plus p of x. And here we can just take this y to the denominator, and we will get y to the power n minus 1 equals q of x, right? So now we can assume that u equals 1 over y to the power n minus 1, and then differentiate with respect to x, both sides. So du by dx equals uh, y to the power, it's the derivative of y to the power 1 minus n, right? So the derivative will be equals to 1 minus n times y to the power 1 minus n minus 1 times dy by dx. So this is the derivative of this function, that is 1 over y to the power n minus 1. So here we get 1 minus n divided by 1, and 1 cancels out, and y to the power n, and then we have dy by dx, right? So this substitution we can just use in the using this equation here. We can substitute here, right? So for this part, that is this thing, we can substitute this thing here. We can move it 1 minus n here, so we can write 1 over 1 minus n times du by dx, that is equals to 1 over y to the power n dy by dx. So now we will substitute this transformation in the standard equation, and then we will get p of x times u equals q of x. And now we can see that this is a linear first order differential equation. By simply multiplying the equation, this equation, with 1 minus n, we can just get the first order linear differential equation, right? So, and then we know that how to solve first order linear differential equations by using the integrating factors. So let's start with the problem. So let's take this problem, that is dy by dx and dy by dx plus y sine x equals y cube cosine 2x, right? So we have this problem. What we need to do is we just need to compare this with the standard form of Bernoulli's equation, and we know that this is a type of Bernoulli equation because here we have q of x times y to the power n form, right? So now we can just divide whole equation with y cube, so we will get 1 over y cube times y prime, and then here we will have sine x over, this is y cube and this is y, so it will go in the denominator, so it will be y squared, and then we have equals to cosine 2x, right? So in this manner, now we can assume that let u equals 1 over y squared, and then just simply differentiate to get du by dx equals to y to the power -2 plus 1, and that will be just like this. First we should write like this, y to the power -2. So this will be equals to -2 times y to the power -2 plus 1 dy by dx, right? So in this manner, here we have du by dx, and this -2 we can move here, so we'll get -1 over 2 is equals to 1 over y to the power, okay, so 1 over, I seems that there is some mistake here, because what we assumed here was, okay, so this is the mistake here. This is n minus 1, not n plus 1, right? So it's -2, -1. So we have 1 over y cubed dy by dx, and we can substitute this thing in place of this one, right? So we can write -1 over 2 du by dx plus u times sine x equals cosine 2x, right? So we substituted these values in the question that was given here, this one, right? The simplified form, uh, this thing here. So in this manner, now we can just multiply a whole equation with -2, and we will get 2u sine x equals -2 cosine 2x, right? So the integrating factor in this case will be equals to a to the power integral -2 sine x dx. So it will be e to the power -2 cosine x. In fact, it will be positive because the integral of sine x is negative cosine x, right? So this is the integrating factor in our case, e to the power 2 cosine x. Now we can just multiply this with whole equation, or just need to write the standard solution form. So here u will be equals to 1 over mu of x, that is the integrating factor. So it will be 2 cosine x times the integral of -2 cosine 2x times e to the power 2 cosine x dx, and then plus c here, right? So now we just need to integrate this function to find the solution, or we can see that this integral cannot be evaluated analytically, so we can just leave this problem here by just putting 1 over y squared in place of u, and then we have 1 over e to the power 2 cosine x times -2, we can move it outside, -2 e to the power 2 cosine x and cosine 2x dx plus c e to the power -2 cosine x. So this is the solution for this problem, and we can leave it here because this integral is that cannot be evaluated analytically. So we can perform some numerical analysis or numerical steps to find these kind of integrals, right? So in this way we can just solve the Bernoulli's equation, and the idea is same for every Bernoulli equation. So we can, if we are able to uh, deduce that the given equation is a Bernoulli's equation, then it's pretty simple to work with the equation, right? So we'll keep this class here, and then we'll uh, do Riccati equation in the next class. So that's all for the time being, and thanks for watching the lesson. Goodbye.